Okay, so let's start with a very simple motion. We will call it rectilinear motion. Rectilinear motion. So we'll talk about the velocity and acceleration of a particle moving along a straight line path. So let's say we have a particle P at time t, and then the particle P moves to point P prime at time t prime equal to t plus delta t, which means that the particle has moved from P to P prime in delta t amount of time, and its position with respect to the origin of a reference frame is given by a single position variable x. We don't need more than one variable because the particle is moving along a straight line, and the distance it travels is delta x. So in this case, we can define an average measure of the velocity when particle moves from P to P prime as delta x over delta t. But this measure is not very useful because most of the time we want to know what is our velocity at a certain instant, not an average measure. So if you're driving your car, your friend calls you, what is your speed? You don't talk about your average velocity. You tell your friend what your velocity or your speed is by looking at the odometer. It's like 55 miles an hour or 65 miles an hour or something like that. Okay. So how do we define that instantaneous velocity? Well, to do that, I have to take my delta t in the limit going to 0. So in the limit when delta t goes to 0, and this is the differential calculus that you learned before, this actually becomes an instantaneous velocity. Right? So I'll just write it instant, but it's essentially the complete word is instantaneous velocity. And what is this quantity defined as? It's defined as dx over dt, or the differentiation of x with respect to time t. So if you know x is a function of time, you can actually compute the velocity at any instant. So let me give you an example. So let's say x as a function of time is given as t squared minus 3t cubed. Okay, and that's given in meters. Okay, so we know this. So if I want to know the velocity at any instant, all I have to do is take the derivative of x, right? So that will be 2t minus 9t squared meters per second. So that's the expression for velocity. So if I want to compute my velocity at any instant, I can compute from that. So velocity at time t equal to 0 clearly would be 0 meters per second. So it's starting with rest. And then velocity at t equal to 1 would be 2 times 9 times 1. So that is equal to minus 7 meters per second. So what is that telling you? It's telling you basically that the particle at time t equal to 1 second is actually moving in the negative x direction, right? So this is the positive x direction, and this is the negative x direction. So we talked about the average velocity, we talked about the instantaneous velocity. Can we do something similar with the acceleration? Sure. So let me draw my frame and the particle again. So this is the delta t time, okay? And let's say the velocity changes going from p to p prime is delta v, then we can define an average acceleration as delta v over delta t. Again, this is not very useful. We want to know what happens in the limit when delta t goes to 0. And in that case, what we get is instantaneous acceleration. And that's an instantaneous acceleration defined as dv over dt. So again, if you know v as a function of time, you can differentiate it once and you will get an expression for acceleration. And if somebody asks you what is acceleration at a certain time at a certain time instant, you can substitute for that time instant in the expression and get the value for the instantaneous acceleration. So this is good. So this is all about motion of a particle along a straight line. Now the question is, can we extend this to a curved path? So motion of a particle along curved paths. Okay, so let's say this is the curved path, right? And here's the particle P. In time delta t, it moves from P to P prime, okay? And we have to have a reference frame, okay? And we say that in this reference frame, the position of this is given by Rp, and it moves from P to P prime, and that vector differential displacement is, let's say, dr. Well, I'm going to call it actually delta r for the reason that will become clear pretty soon. Okay, I'll call it delta r, okay, to be consistent with how we're defining the differential change in displacement. So how do we define average velocity? In the same way we did before, average velocity is nothing but delta r over delta t, and in the limit when delta t goes to 0, delta r over delta t actually becomes instantaneous velocity, right? And so instantaneous velocity, and I will skip the subscript instant, I'll just write simply v, is nothing but dr over dt. So if you know r as a function of time, which could be given as x t I hat plus y t j hat, right? So we have two components, x and y, both of them are function of time. And this is clearly the motion of a particle in xy plane. If this was moving in a 3D space, you will also have a third component, let's say zt, along k hat direction, right? So if you want to get the instantaneous velocity, all you have to do is differentiate it once, and you will get your instantaneous velocity. Similarly, the acceleration at any instant would be defined as dv over dt. So if you know velocity is a function of time, you can compute the acceleration as well. Okay, so let's do a simple example. So let's say I am given the position of a particle r as a function of time to be t squared minus 2t I hat plus 3t squared minus 1 j hat in meters. Okay, I'm just making up an example over here. Clearly, the position of the particle is dependent on the time. At time t equal to 0, it's someplace, and time t equal to 1 second, it may be somewhere else. And we are interested in finding what the velocity is and what the acceleration is. Okay, so to get the velocity, all I have to do is differentiate r. So what do we get? 2t minus 2 I hat plus 6t, and minus 1 differentiate would be 0. So we get that. And this would be, assuming time is in second, meters per second. Right? So that's the whole expression for the velocity. What about acceleration? We can get acceleration also by differentiating velocity. Right? In other words, this is actually second derivative of r. Right? Okay, so let's differentiate velocity, which is right over here. So we get 2 I hat plus 6 j hat meters per second squared, right? So that's what we get for the acceleration. So if I ask you, tell me, is the acceleration constant? What would you say? Well, clearly there is no time in the acceleration expression, which means that acceleration is constant, right? So what's its magnitude? We can compute that. Magnitude of the acceleration would be square root of 2 squared plus 6 squared, which is square root of 4 plus 36, or square root of 40, and you can compute that, meters per second squared. That's the magnitude. What is its direction? You can compute that too. So if you want to draw this is x-axis, this is the y-axis, then we know that the angle that the acceleration is making can be opted as, so tan theta would be equal to 6 divided by 2 or 3, right? So if you compute the inverse of 3, that will tell you the direction that the acceleration vector is making from x-axis at all times. Okay, so now that we have seen that if we are given the position vector as a function of time, we can compute the velocity and acceleration. Let's look at what are the general directions of velocity and acceleration. So let's start with direction of the velocity. What is the direction of velocity vector? In general, when a particle moves along a curved path, we know if it is moving along a straight line path, then the direction of the velocity is same as the direction of the movement. But when a particle is moving along a curved path, then the question is, what is the direction of the velocity vector? Okay, so if you're saying that the velocity vector should be tangent to the path, then you are absolutely right. But the question is, can we see that? And the answer to that question is yes. It's actually pretty easy. So let's say we have a reference frame, okay, and we know that this is the position of the particle at one instant. After a certain instant, the position will change, and let's say that's the new position vector r prime, right? So this is the delta r, the change. So let's zoom in over here, right over here. So I'm going to draw this in a separate color so that you can see it clearly. So here's a point P, here is a point P prime, right? And that's the delta r, okay? And the path was something like this, let's say, between P to P prime. So when we want to talk about the velocity vector, right? What is velocity defined as? The velocity is defined as limit delta t going to 0, delta r over delta t. right? So in the limit when delta t is very, very small, then we opt in the instantaneous velocity. But what happens when delta t actually goes to 0? Well, when delta t goes to 0, the point p prime is actually very close to p, right? So let's say, delta t was half, then where would the particle p be? Well, it would be somewhere here, let's say at p prime, right? And that would be the delta r then. In the limit when delta t goes to 0, this velocity vector actually becomes tangent at point P, right? You can see this is the variation. This is the variation. So as delta t is going to 0, the velocity vector is actually becomes the delta r vector becomes tangent to the path, right? And that decides what the direction of the velocity would be, because this quantity is actually a scalar quantity. In the numerator, you have a vector quantity. So whatever the direction of the delta r is will decide what the direction of the velocity is. So we can say that v is always tangent to the path, right? We can always say that v is always tangent to the path. Now, tangent to the path is usually a line, so the direction of the movement will decide which way it would go. So whether it will go, this way, or whether it will go that way. Okay, so velocity is always tangent to the path. That's something that you should always remember. Okay. All right, so what about its magnitude? Let's talk about that as well. So we know that v is defined as dr over dt. Okay. Now, in the limit, when delta d goes to 0, actually delta r, which is the differential displacement, is nothing but the total distance traveled along the curved path, right? So in the limit, when delta t goes to 0, delta r is nothing but dr, right? And its magnitude is actually nothing but the distance traveled along the path, right? So if I take the magnitude of v and I write something like this, what do we get? We get ds over dt, where ds is the distance traveled along the curved path. And magnitude of v we'll simply write as v. Okay, so there's no half vector on top or full vector to indicate it's a vector, so it's a scalar quantity. So speed is defined as ds over dt. Okay, so that's the magnitude part of the velocity, which we call speed as well. Now let's talk about acceleration. So let's talk about acceleration. And in particular, we want to understand what the direction of the acceleration would be when a particle moves along a curved path. So let's say, we have a particle moving along a curved path like this, all right? So particle is here, and then after a while, the particle may be here, let's say at P prime, right? Now, what is acceleration defined as? Acceleration is defined as dv over dt, which is nothing but change of velocity over time, right? So velocity itself is a vector. A vector has two components. It has a magnitude, it has a direction. So when we take differentiation of velocity over time, we also want to know if the magnitude of the velocity is changing, or the direction is changing, or both of them are changing. If either of them are changing, if either the magnitude or the direction are changing, then the acceleration would be non-zero, right? If both the magnitude is not changing, if both the magnitude as well as direction are not changing, then clearly the acceleration would be zero. Okay, so let's talk about what the direction of the acceleration would be. So let's say, here is the particle at one instant at a point p prime. Its velocity is, let's say, v prime. If, let's say, going from p to p prime, the speed change. So if v and v prime are not same, so if v prime is not equal to v, so if v prime is not equal to v, then clearly there will be a component of the acceleration which will be non-zero, and that will be due to change in speed. Okay, but even if, let's say, v prime and v were same, even if their speeds were same, in this particular case, in this particular diagram, the acceleration would still not be zero, even though their speeds are same, because the direction of the velocity vector has changed. So at this instant it's pointing this way, at this instant it's pointing that way, and clearly the directions of the velocity vectors have changed, and that means again that the acceleration would not be zero. So even if v prime is equal to v, acceleration is not equal to 0. So in this case, it's not equal to 0. And even if v prime is equal to v, acceleration is not equal to 0. Now, what we want to understand is, if, let's say, the velocity magnitude or the speed was same going from P to P prime, which way this acceleration vector would be pointing. And that's easy to see because we know acceleration is defined as dv over dt, right? And what's dv? dv is basically change in velocity. Change in velocity is always change in anything in differential calculus is defined as final minus initial, right? So it could be final velocity minus initial velocity, final position minus initial position, and so on. So dv over dt is basically given by change in velocity, so which is v prime minus v, right? So if we draw these two vectors together, so here is v prime, so I'm just transferring this vector from here to here, okay? And then what's minus v? So we want to do v prime minus v, so that's same as v prime plus minus of v. So this is how v is pointing. So minus v would be pointing in the opposite direction, right? And that's basically, minus v over here transferred. So v prime minus v, this is minus v, their sum would be given by, you can use parallelogram, and that would be the resultant. And this is v prime minus v. And you will notice that, when in this particular case, v prime minus v, which is the resultant of v prime and minus v, is pointing towards the concave direction of this path, right? So this is how the path looks like. It's pointing towards the concave direction of the path. And that is how the acceleration vector always points, okay, even if the speeds are same. Now, if the speeds are different, then there is a component of acceleration along tangential direction. And this is the component that points towards the concave direction. And we will see pretty soon that actually this acceleration vector is perpendicular to the tangent direction. Okay, and it's not clear over here exactly how it is perpendicular, but in the next half an hour it'll become very clear as to how it is, where it is pointing. Okay, so it's always pointing towards the concave direction. If the path was this way and here was the particle p, and even if it was moving at constant speed, the acceleration would be pointing towards the concave direction.